going to do that. Okay, so to begin with, we're going to use an integral, and we're going to base it on this curve right here, and we're going to try to show that the area of a circle is pi r squared. Okay, in this case, pi a squared. There's a couple of things I want to show you on this. First of all, that this curve right here that you see right there that's an equation of a circle with the upper part of it with the square root. So I want to kind of show you at the side kind of where that comes from before I start into the work, setting up the integral and doing that. So like if you have, you guys know from your background, hopefully, that x squared plus y squared equals r squared. Okay, that's a circle with the center at 0, 0. You guys remember that okay? All right. Now what I'm going to do on this is I'm going to change the r squared to a. I'm just using a. I'm just following what this, I could use r though if I wanted to. So I'm just going to use that like that. A is going to be the radius of the circle in here, because that's the distance from 0, 0 to that point on the graph. And then if I solve this, you know, for y squared, I would, you know, move the x squared to both sides, take a square root of both sides, then I'd have technically y equals plus or minus square root of a squared minus x squared. So I just want to show you that that is you can think of that as a circle, okay, like that. Okay, so what we're going to do is we're going to try to set up our integral with this, and one thing that we're going to look at on here is the area of the circle that we're going to do right here is going to be 4 times the integral, and we're going to do an integral of this function. Now it's 4 times that because this is just like a fourth of a circle, right? Okay, so what we're going to do on that is we're going to do the integral of a squared minus x squared dx. We're going to integrate that from 0 to a. So if we can figure out what that integral is, then we will quadruple it, and then we should have a formula for the area of a circle. So one thing's kind of interesting with calculus, you can develop all kinds of formulas that we know from geometry anyway by integration. So this is a trig substitution integral, so I'm going to have you draw a triangle. As you're doing your trig substitution, as you're learning this, you can kind of refer to these triangle diagrams. So since you have a squared minus x squared, okay, that is the sign substitution. Okay, so what I'm going to do on this is let's just go ahead and draw a triangle, kind of going like this. So this is going to be your angle theta, and this is x, that's a, and then that's the square root of a squared minus x squared. Now all of those things are related by the Pythagorean theorem. We talked about that last time, but I just want to remind you that if you did, you know, this side squared plus this side squared, you would get a squared. Okay, I'm just doing a squared plus b squared equals c squared, really, from Pythagorean theorem. I just want to show you that that's a squared minus x squared. Radical comes off. Okay, so they're all the same. Okay, so that satisfies the conditions of the Pythagorean theorem. All of these triangles that we're going to use in these trig substitutions come from the Pythagorean theorem. Okay, so what we want to do next here is we want to develop from this triangle. There's 2 things you want to do. First of all, the sine of theta. What's the sine of theta in the triangle I just drew? Opposite over hypotenuse, so what is it? X over a, good. Okay, so that's x over a. You got to go back, you got to know your trig definitions. That's real important in this section. Then I could multiply both sides. You can do this in your head. You don't have to show this really. You can multiply both sides by a, so you get the trig substitution, x is equal to a sine theta. Okay, and that's what that triangle diagram they have in the book is going to give you. Okay, then what you want to do is, so what's going to happen is in this integral we're going to do, where you see an x, that's going to get replaced with a sine theta. Okay, and then we got to figure out what dx is. So we just do the derivative to do that. So dx, what's the derivative of a sine theta? A cosine theta, right? Okay, we're doing a derivative of the sine, which is the cosine, right? So a is a constant, so just write that down. So that's cosine theta. So then what you're going to have is in this integral, you're going to replace dx with a cosine theta, then you're going to have your basic integral put together. Okay, like that. All right, do you guys follow what I'm doing so far? Okay, mostly in this section we're dealing with trig substitution integrals. This is just an application of finding an area of a circle. Okay, so let's do the area of the circle then. So remember, what we're going to do is we're going to do 4 times this integral from 0 to a. Now what we're going to do is we're going to replace the x squared with a sine theta. So a sine theta goes there. Okay, so I'm going to plug that in. Okay, and then the dx is going to get replaced with times a cosine theta right there. Okay, and then that would be, I need to have a d theta at the end like that. Okay, so we got everything substituted in the way that we want to substitute. Okay, does that make sense as far as the substitution? Okay, now the reason this works so well, once you kind of start working out these problems, you'll see how they work. You end up usually having that square root kind of goes away because you end up using identity. So let's go ahead and proceed with this. Now we're just ready to just crunch out the integral. So we're going to do 4 integral 0 to a. Okay, under the radical I have a squared minus a squared sine squared theta. Just multiplying that out. Then I have times a cosine theta times d theta like that. Now I'm going to keep just kind of crunching that out. Okay. Now if you look under the radical, what could you do under the radical? What do you see? Yeah, you can factor an a squared out. That's one thing. So you want to go ahead and take that a squared out. And then that would leave you with 1 minus sine squared theta. Like that. Okay. Now, what could you do with 1 minus sine squared theta? That's a cosine square. See, that's an identity, right? Okay, so you have that fundamental Pythagorean identity. You don't need to write this down, but just to remind you, sine squared theta plus cosine squared theta equals 1. You're going to use that identity when you're doing these trig substitutions. So we're going to change this to 4 times the integral from 0 to a. And we're going to have a squared cosine squared theta times a cosine theta d theta like that. Okay? Now, what happens to that radical? Becomes what? A cosine theta, right? If you do the square root of something squared, it undoes the square, right? So now we kind of end up with a simplified integral. We're going to integrate from 0 to a cosine theta, that comes out of the radical, times a cosine theta like that. Okay, so once you kind of do that trig substitution, what you have is that's typically what happens. Okay, is generally that radical goes away. Now this thing is a constant, so I'm going to go ahead and pull that out of my radical. A times a is a squared, so that's going to give 4a squared integral 0 to a, and then that will leave us with cosine theta d theta like that. Okay, let me pause there for a second and see if we've let you kind of catch up with your writing down and see if you got any questions about anything I've done there. Okay. All right. So again, since it's an a squared minus x squared integral, that's the reason we did this sign substitution. Okay. Now we've learned how to do powers of sines and cosines. So do you guys remember what you would do to integrate something like cosine squared theta? What do? You use a half angle identity, exactly. Okay, so I'm going to use that half angle identity. The half angle identity for cosine is cosine squared theta equals 1 plus cosine 2 theta over 2. Okay, you don't need to write that down. I'm just referring to that. So what we're going to do now is we're going to replace this with 4a squared integral 0 to a. Now replace that cosine squared with 1 plus cosine 2 theta all over 2 theta d theta. Okay, like that. All right. And that's what you typically are always going to do. If you're integrating a sine squared or a cosine squared, you want to pull out that half angle identity. Okay, so we've done that. Okay, so let me go ahead and let's move this kind of over here. I'm going to move this up here for a second. And then we'll go ahead and get that integrated. Then we do have to work quite a bit out on the definite integral. Okay, so if you integrate this, and we've done this several times, what you would be doing is you would really be just looking at breaking this up into 1/2 plus 1/2 cosine 2 theta d theta, like that. Okay, now we're pretty much ready to do our integral finally after all that rearranging. So there's about 7 or 8 steps just to get to that point. Okay, so now we're ready to do this. All right, so what's the integral of 1/2? Now we're talking about theta now as our variable. So what do you have? 1/2 theta. Okay, then when we do the next part, we have 1/2. What's the integral of cosine 2 theta? 1/2 sine 2 theta, right? Okay, if you differentiate a sine, you get a cosine. So that's going to be 1/2 times, and then that's going to be sine. Whoops, hold on, I got one more thing I got to put there. Okay, I got the 1/2 as the constant, and then when I do the integral of the cosine, that's another half, and that's sine 2 theta, like that. Okay, and then that whole thing's going to get evaluated from 0 to a. Okay, so let's clean this up a little bit and see what we have. So we have 4a squared, and then I have 1/2 theta plus 1/4 sine 2 theta integrated from 0 to a. We're going to evaluate the integral from there then. Okay. Okay, so that's my integral. Now I got to start evaluating. Is there any questions so far on this? Is that making sense? You typically, when you do these trig substitutions, you have identities that you almost always end up using, and then you end up transforming it into something that you can integrate pretty easily, actually. Okay, so now let's go ahead, and the rest of the problem, I'm going to go ahead and just start focusing on the evaluation of the integral now. Okay, so the fundamental theorem. So we have 4a squared. Okay, then I'm replacing all the thetas with a, so I'll have 1/2 a plus 1/4 sine of 2a, like that. And I got to do the 0 part here. Let's see what that leaves me here. Remember, we're trying to get pi a squared out of this whole mess. If we get pi a squared, we're good. I already know what the answer is supposed to be because we're finding an area of a circle. So now it would be 1/2 times 0 plus 1/4 sine of 2 times 0. Okay, like that. And then we just have to crunch out the details. Okay, so let's see what we got here. So we have 4a squared. Then inside the parenthesis here, I've got 1/2 a. Now, here's something that you want to kind of think about here a little bit. Any suggestion about sine 2a? Sine of a double angle. Do you remember anything from trig about that? It's an identity, right? The identity goes like this. So here's another identity we're going to use in this problem. Sine 2 theta is 2 sine theta cosine theta. Okay, that identity shows up quite a bit. And we're going to go ahead and just substitute that in, and I'm just going to kind of see what happens with that. Okay, so what I'm going to do is I'm going to go ahead and change that to 1/4, and then I'm going to change that to 2 sine a cosine a. Okay, like that. So I want to kind of work with that a little bit there. Okay. Then what I'm going to do from here is in this, whoops, I need to go like this. So from here I'm going to have 0 there. Then I'm going to have plus 1/4 sine of 0, like that. So let's see if I'm getting anywhere with this problem. Okay. All right, so let's see what we got now. So now what I'm going to have is from this stage, it looks like I'm going to have, I'm going to go ahead and just sort of multiply some of this out. I'm going to go ahead and clean up what's in the brackets here. So it looks like 1/2 a plus 1/4, and actually I see a little cancellation there. The 2/4 is going to reduce to a half. So that's going to be 1/2 sine A cosine A, like that. And then I'll have minus, and see this thing right here, see the sine of 0 is 0. So that whole thing right there just becomes 0. Okay, like that. So now we've got that kind of worked out like that. Now I'm going to multiply it out. Now the thing is, we're trying to get, we got to go back into our triangle a little bit here, and we got to do something a little bit with that also. Okay, so we're getting pretty close to being done with it. Okay, so what we want to do with this now is if you go back to this trig substitution. Now I'm going to go ahead and just distribute this out real quick. So this is going to be 4a squared times a half a is going to be 2a to the third. And then if I do this, 4 over 2 is 2, so I have 2a squared. Then I have sine a cosine a like that. Now the thing about this is I've got to look at my triangle. So I need to go back and work a little bit with the substitution right here then. Okay, like that. Okay, anything so far? Any questions so far? There's probably something I could have done a little bit earlier in here, and what I probably, when I had that theta, you got to write that theta back in terms of your variable x here. So let's see, if I take it from here, there's a couple of ways that I think I could do this, but I'm kind of, as I'm doing this, I thought there's a better way I could have gone from this point. So I may go back and just kind of and fix that. It may be better to do it this way then. I think it'll work out this way, but what I'm going to go ahead and do is, if you look at this piece right here, where I have that double angle identity, I'm going to go back and I'm going to do something a little differently. Okay, I kind of got a little off track there, so I'm going to change one little piece of it. Okay, is that okay? Okay, all right. It'll work this way, but it's a little more complicated. So I didn't see what I should have saw, and I'm going to just kind of stop there. You can just scratch that out or erase it if you want to. My apologies. There's just something a little easier you can do here. So what I'm going to do at this stage is I'm going to go ahead and I'm going to write this as 4a to the second like this, then 1/2 theta. I am going to use this identity right here because that's a little bit easier. So I'm going to have 1/4, then I'm going to write this sine 2 theta is 2 sine theta, cosine theta, like that. Now what I'm going to do at this stage is I'm going to go back and I'm going to kind of look at my triangle. One of the things you got to do in these problems a little bit is you don't want theta to be a part of what you're working with. So and then we're going to evaluate this thing in a few minutes from 0 to, I've already done the 0 to a like that. Okay, so I need to kind of slide that in like that. Okay, now going back to the triangle, I'm going to just refer to my triangle and show this to you a little bit. Okay, now what we need to do is we need to write this back in terms of x. Okay, and I'm going to do that, then I'm going to evaluate my integral, then it'll work out okay. So if you look at this trig substitution right here, if you look at this piece where you have x is equal to a sine theta. Now I'm going to write that in terms of theta, okay? So one thing I can do on this is I can divide both sides by a, so I get x over a is equal to sine theta. Now my goal right here is figure out what theta is, okay? Can you guys tell me what theta would be based on that statement? This is a little trick. Inverse, right, okay? Now one of the things you can do that in your head, or you can take the inverse of both sides, like this. Okay, so that would give inverse sine x over a is equal to theta. So that's what I'm going to plug in there, is that inverse sine, like that. Okay, and this is before I evaluate my integral and everything too. Okay, so what I'm going to have, okay, is this. This is getting a little sloppy. So this is 1/2. I'm going to replace theta with that thing. So right there, you want to replace that with this thing. So that's going to give inverse sine x over a. Okay, then here, those are going to cross out to give 1/2. And then we need to figure out what sine and cosine theta is like that. Okay, you guys following? It's just kind of an interesting problem. Like, it's kind of a hard one. There's two other things we want to do here now. Okay, I want you to look at the diagram. Tell me what the sine of theta is in this triangle diagram. It's x over a, right? It's opposite over hypotenuse, so that's going to be x over a. Okay, now I want you to tell me what cosine of theta is in this diagram. It's adjacent, which is this, over hypotenuse, right? So that means the cosine is going to get replaced with that over that. Okay? So what we've done now is we have adjacent, square root of a squared minus x squared over a. Then we're evaluating from 0 to a. Now the reason I did that is you need to express this back in terms of x. Now we're back in x. Now what we're going to do is we're finally going to evaluate the integral using the definite fundamental theorem to finish that up. Okay, you guys following this or not? At least somewhat? Okay. All right. So now we're ready to go through and we're ready to plug in a. Okay. And remember, we're trying to get 4a squared out of this. So I think I'm on track here. So, all right. So I'm going to go ahead. We have the 4a squared here. I'm going to draw like a real big bracket here. And I'm going to, everywhere I see an x, I'll have you plug in an a. Okay, so everywhere we see an x, plug in an a. You're probably going to have a lot of things canceling when you do this then. So that's going to be 1/2 inverse sine of a over a, which is going to be inverse sine of 1. Okay, this piece I'm just going to write that as 1/2. And let's see, x becomes a, so that would be times a over a. And then this thing is going to become a squared minus a squared all over a. Okay, so that's plugging in the a. You're going to see a bunch of things kind of working their way out of the work there. Now we're going to plug in a 0. So everywhere you see x, now you want to plug in 0. So we're going to have 1/2 inverse sine 0 over a plus 1/2 times 0 over a, which is awesome. That's going to cancel all that out. So that's going to be a squared minus 0 squared over a like that. Okay? So now let's see if what happens out of this big mess here. Okay? All right, so here's kind of what I see on here. It looks like we got a 4a squared. We have a 1/2. Now, if you look at this piece right here, just that piece right there, that is a inverse sine of 1, right? Go to a unit circle, just think in your mind, where is the y value equal to 1? Pi over 2, right? Okay, so there's our pi. Okay, we knew we had to get a pi out of this mess somehow, so that's pi over 2 is what that is. Okay, now what we have here is it looks like, see this thing's 0. See right there? That whole thing is 0. So that means that whole thing goes to 0, right? That whole thing right there is gone. Everybody see that? Because you have a squared minus a squared, which is 0. Okay, now you go here, and when you go to this piece right here, this is really going to be inverse sine of 0. So where on the unit circle is the y value 0? At 0, and within the range of an inverse sine, that would be 0. So that whole thing right there goes to 0. So now you have this. You have minus 1/2 times 0, and then that whole thing's 0. Because you have a 0 over a, so that whole thing gets multiplied, so you get this. All right, I think we're in business now. So it looks like what we have is 4a squared times pi over 4, and then the 4's cross out. So we got pi a squared. Hallelujah. I was afraid I'd make a mistake on that one. That is a lot going on that. And then the purpose of that, it's not something I'd ever test you on, but it's just showing you that how you can use an integral to develop, to not really to prove some sort of a formula. So we got pi a squared. Okay? Did you guys get the gist of what I did there? Okay, if you follow, that's pretty good. I mean, it's messy. I mean, you know how these problems are getting now. That's how it gets in Calc 2. So that's just something I wanted to do is a little bit different with a proof. And you can do, you know, stuff like you could derive. You guys are at the level where you could derive like the formula for the surface area of a sphere or the volume of a sphere by rotating around axis. Okay, so those are kind of cool things to do. Okay, so let's do this. Now this is kind of back on, you know, what I want to make sure that you know how to do. We haven't done a secant substitution yet. So on this example 5, we're going to go through and now look at a secant substitution. So what you have to do is you got to match what you have. So this is the triangle. As you're doing your problems, you can refer to the 3 triangles that are later in your notes. And since it's x squared minus 9, if the x comes first, it becomes a secant substitution. If the a comes first, it's a squared minus x squared, then it becomes a sine substitution. Okay? So the first thing we want to do with this one is we want to get the triangle drawn and the substitution kind of done. So what I'm going to do on this is write this kind of like this. So let's draw out a triangle, and then we'll get our substitution put together like this. So theta is always that kind of base angle. Now, what we're really looking at is we're looking at the integral of x squared. 9 is a perfect square, so you want to write that as 3 squared over x dx like that. Okay? Now, if you just strictly follow the diagram right here, what you're going to have is a is what's being squared. So that a is 3, so that's going to go there. Okay? X is going to go there. And then this is going to be left with x squared minus 3 squared like that. That's Pythagorean Theorem, okay? Now, one thing that you guys need to be solid on, you need to understand this triangle. So, you know, if you wanted to find a missing side of a right triangle, you do the Pythagorean Theorem, right? So this thing right here would just be this squared minus that squared with the square root of the whole thing. Does that make sense from Pythagorean Theorem? So that really is all related in the Pythagorean Theorem. That's how I remember that if I have a minus, that it's one of these legs of the triangle. It's got to be. That's a hypotenuse. So that would be more like x squared plus something. That's a tangent substitution, which we'll do a couple of those here in a little bit too. Okay, so we're set up. Okay, get your triangle out. You want to make sure you're set up. Now you're ready to do your substitution. So first of all, in this one, we're going to do a secant. So the secant's definition, a secant of theta is hypotenuse over adjacent. So tell me in this diagram what the secant of theta would be. Hypotenuse over adjacent's what? X over 3, right? Okay, so it's a secant substitution. So we're going to say x over 3. Okay, now you can multiply both sides by 3, and you're welcome to do that in your head. So you would get x equals 3 secant theta. Okay, that's what that main substitution right there is then. So what that's going to mean is in our integral, everywhere we see an x, there's 2 places we're going to have an x. We're going to replace that with 3 secant theta. Okay, then the other thing you got to do is you got to do dx. Okay, what's the derivative of the secant? Secant tangent. Okay, these things show up from here and there. So you got to be on top of that when they do. So that's going to be 3 secant theta, tangent theta, d theta like that. Okay. So what that's going to be is that gets plugged in here. So that thing right there is the dx that goes in there. Okay. So now you want to go ahead and just see if you can get everything plugged in. And then we'll be ready to kind of put together our integral and see what we got here. Okay. So when we do the substituted one, let's go ahead and get everything substituted in now. So we're going to have the integral of square root. Okay, x is going to get replaced with 3 secant theta squared. And you can go ahead and write that as a minus 9 if you want to now. Okay, and that's all going to be over x. So again, x is 3 secant theta tangent theta, like that. Okay, now the dx is going to get replaced with, whoops, I put the wrong thing there. X is 3 secant theta. Okay, so I think I got everything in there right. Now dx, you want to replace that with 3 secant theta times tangent theta times d theta, like that. Okay? All right, does that substitution look okay to everybody? Okay. Now, what you're going to do with this, you want to start kind of cleaning stuff up. It takes a few steps before you're ready to start integrating, and you'll kind of begin to see the pattern that exists on this. I'm going to square this thing out there, so that's going to be 9 secant squared theta minus 9. That's what's under the radical. And then notice the 3 secants cross out, so by all means, just cross them out. That's nice when that happens. And that's part of the reason this substitution works well. And then we'll be left with times tangent theta d theta, like that. Okay? All right, what should I do under the radical? Factor a 9 out, and then you're going to think about an identity. That's what typically is what you do. So now you can go ahead and factor the 9 out. That's a perfect square, so that kind of helps us. So that would be secant squared theta minus 1 times tan theta d theta. Now remember, what you're hoping is that radical goes away. Okay, so you have an identity. I'll just kind of write the identity at the side here. So we have the identity that goes secant squared theta plus 1 is equal to tangent, or no, I always do that backwards. I always have to derive this in my head. I don't know why I never can remember this identity, but I always have to do this in my head. So that goes, let's see, sine squared plus cosine squared equals 1. It's not bad to show you how I derive this. This is kind of what I do is that. I divide by a cosine squared, so I get tangent squared theta plus 1 equals secant squared theta, like that. Okay? One of these days I need to just crack down and remember that thing. But for whatever reason, I never can remember how that goes, so I have to derive it. So what I'm going to do is I'm going to move the 1 there, and I'm going to get tangent squared theta equals secant squared theta minus 1. Okay, so that means that I'm going to replace this thing with that. Okay, and then that'll take you out of the radical then, see. Okay, so we're going to go ahead and plug that in. And then we're getting close to a point where we're ready to go down and do the integral. So that's 9 tangent squared theta times tan theta d theta, like that. Okay, what's that square root become? Okay, 3 tangent theta. Okay, so that's going to give us the integral of 3 tangent theta times tangent theta d theta. Okay, so that'll give us an integral of, and then you can bring the 3 out since it's a constant. So that will give us 3 times the integral of tangent squared theta d theta, like that. All right, so that is the trig substitution part. Now we're ready to integrate. So is that clear to everybody? Okay. Now we've come across the integral of the tangent many times. What do? We break it down into this identity. Okay, this identity right here turns out to be very, very useful. We're going to use it again. So, and the reason is, do you know what the integral of the secant squared is? That's tangent, right? Okay, do you know what the integral of 1 is? Yeah, that's x, or theta in this case, all right? So that means what we're going to do is, next step, we want to go ahead and write this as 3 times the integral of secant squared theta minus 1 d theta, and then we can go ahead and integrate this now. Okay, so that's going to be 3 times the integral of the secant squared is the tangent theta now, and then the integral of 1 is theta, like that, and then we have the plus c, like that. All right. Okay, now we're done with the integral, except there's one key thing that you have to pay attention to here now. And don't forget this now. See, our answer is in terms of theta, right? The original integral had x's in it. So what you have to do is you have to change these variables back to x. So watch this very carefully how I do this. Okay, first of all, I got to figure out 2 things. I got to figure out what theta and what x is in terms of the triangle in terms of x. So first of all, if you go back to your triangle, okay, the tangent of theta, go back to this triangle right here and tell me what the tangent of theta is. It's opposite over adjacent, right? So that would be this over this. Okay, so the tangent of theta is going to be square root of x squared minus 9, like that, all over 3. So that's what's going to go there. That's what we're going to plug in there. Okay, now go back to your substitution. Okay, your substitution is x is equal to 3 secant of theta. Okay, so we now know that what to use for the tangent. So we're going to plug that in. Now, when you do this, divide both sides by 3. So you'll have x over 3 equals secant theta. So can you tell me what theta is now? It's the inverse secant, right? Okay, you're doing an inverse secant of both sides. You can do that in your head. So what you're doing is when you do the inverse secant of both sides, you get inverse secant of x over 3 is equal to theta, like that. Okay, so now when we're ready to write our answer, we've got, again, we got 3 tangent theta minus theta plus c. What we're going to do is just replace the tangent with what it's equal to, and replace theta with what it's equal to, and then we're done. So that will give us 3 times square root x squared minus 9 over 3 minus theta, which is inverse secant x over 3 plus c. Okay, and then that should be the final answer to the problem. There's one other thing that you could do on this. If you look at this, you probably want to go ahead and just distribute the 3 through there, because that'll cancel a 3 out. So let's do one more step and write the final answer as square root of x squared minus 9, with those canceling, and then minus 3 inverse secant x over 3 plus c. Okay, so that's it. A lot of work. It's not too bad, though. The key is getting all those substitutions put together when you do this stuff then. Okay, you guys follow that or not? Okay, so I think what I've done is I've done several of the sign substitution. That's a secant substitution. And I think I want to kind of look at maybe a tangent substitution here. And I think the next page, what I have is, this is just basically taken straight out of the book. These are the things you can refer to. This is the sine, tangent, and secant substitution. Those are the 3 that you're learning. You can look at the substitutions. I think it's just mainly identities. You want to make sure that you know your Pythagorean identities from trig, and that's kind of a key. Another thing, these are just kind of reminders. You don't need to write anything on this page, but a couple of things, like for instance, you can write this down if you don't remember this, but the ranges, they do show up a little bit. So like the range of an inverse tangent goes from negative pi over 2 to pi over 2. We've seen that a little bit when we're working out integrals. The inverse sine is bracket negative pi over 2 to pi over 2. And the inverse tangent, if that, I just wrote that twice. The inverse cosine, its range goes from 0 to pi, like that. Okay, I'm just going to focus mainly on those 3 right there. Okay, so those are a couple of things that you want to pay attention to, and this is kind of a good summary of what you want to have down. Okay, any questions about anything so far? Okay, I think the only thing I hadn't done is I hadn't done a tangent substitution yet. The next page just kind of, this probably you won't encounter this very much, but this one also just has a statement about an inverse secant's range, which goes like this. And this is really ultimately what you want to kind of have down, because since you're doing a secant substitution, the range of an inverse secant goes like that, and I'll kind of tell you how I remember this. Okay, so basically in interval notation, what it does is it goes from, and it's kind of similar to the cosine. So generally what it does is it goes from 0 to pi over 2, but it doesn't include that. And then it goes pi over 2 to pi like that. Okay, now, the way that I remember this is the range of an inverse cosine, you may remember from trig because it's more common, is 0 to pi. So, the thing on this is notice that I left off the pi over 2. What do you suspect the reason for that is? Has something to do with the secant at pi over 2. Let's see what's happening. So if you look at pi over 2, you have the point 0,1. So notice that if you do the cosine of pi over 2 is 0, right? So what would be the secant of pi over 2? Since it's a reciprocal of the cosine. It'd be undefined. Okay, so basically the idea with that is since the secant of pi over 2 is undefined, you want to kind of make sure that you pay attention to that if it ever shows up. Okay, that's kind of that's how you write the range of an inverse secant. Okay, all right. Any questions? Okay, let's do a tangent one. This one I think has a typo on it too. I think sometimes when I export my files, they don't work right. So one thing you need to do is this was supposed to be an 18. So go ahead and put an 18 in there. It'll work if I left it at 1, but it'd be pretty messy. Does it say 18 on it? Okay, it probably just didn't export to OneNote when I did it. Okay, so this one is a tangent substitution. So, you know, I've just put the triangle on here so we can kind of refer to this as we go. So what you're used to doing on a problem like this is completing the square. So it looks like before we do anything, that kind of looks like a completing the square integral, doesn't it? Okay, so we're going to go ahead and work out, just kind of before we do the substitution, we're going to do the completing the square and just review how you do that. Okay, then we're going to do a trig substitution on this one actually. So let's see, we have x squared plus 6x. Going to complete the square on that. That's an 18. Okay, so if you take half of 6, that gives 3. If you square the 3, you're going to get a 9, so you want to put a plus 9 there and a minus 9 like that. Okay, and then when that factors, that's going to be x plus 3 squared, whoops, not cubed, squared, and then plus 9 like that. So it's kind of got the same type of format that we're used to seeing then. Okay, so what we're going to do with this one then is we're going to rewrite this integral kind of like this. Okay, when I do this, I want to go ahead and rewrite this as the integral of dx, and then I want to write this as x plus 3 squared plus 9 like that. Now that looks like kind of a u substitution integral, doesn't it? And we've done this integral, we just haven't done it with this technique. So we're going to look at this with a little bit different technique. Okay? All right. So everybody okay so far? Completing the square. We've done that, right? Okay, let's do u substitution. What would be a good thing to set u equal to in this problem? X plus 3. Okay, we're going to try to turn this into a squared plus x squared kind of form. So let's let that be u. So u is x plus 3. Okay, like that. And then that means that du is going to be just dx. So we're ready to go ahead and substitute everything in then. Okay, so when we do our u substitution integral, we're going to have this. Dx is going to become du. Okay, so we should have du over u to the second plus 9, kind of like that. Okay, now I'm going to do a triangle on this, but I'm going to do, with this one, I'm going to do the triangle, you know, a little bit differently without the square root like this. So we've done this one before. We even learned a formula, an arctangent formula that'll get this to you. So let's go ahead and let's draw out our triangle on this one now. Okay, like this. And the way that we typically want to do this now is kind of like this. All right, so, and we would want to go through and look at this one kind of like this. So when we do this, we're going to have if you look at the setup on this, we would want to kind of have the u here like that, and then the 3 there like that, okay? And then what would go here then would be the square root of 3 squared plus u squared like that. Okay, now we can kind of do something with this one. I think what I wanted to do on this one now is, since that's not under a square root, okay, we would want to go ahead and kind of work, see if we could work with any sort of a substitution there. Well, see, that thing's not under a square root, so you could go ahead on this problem if you wanted to, and you could go ahead and just use that general formula we used, which was the 1 over a arctangent of u over a. Okay, and do that if you want to. Okay, because see, that doesn't have a square root in it. But so if you set that up, since that's lacking a square root, one way you could go ahead and finish this up is it just goes like this. The formula we learned is basically 1 over a, which is 3, and then that was arctangent of u over a plus c like that. So that's the way that we learned how to do that. And then what we'd have from here is we'd have 1/3 arctangent, and then u is going to be x plus 3. So then you could plug that back in like that. Okay, so if you do that, you would have x plus 3 over a plus c, and see, that's what we learned how to do earlier in the semester, is that approach like that. Okay, now so is there any question about, you know, how we learned how to do that in the past with this, with that basic form? Remember, we learned basically the formula for u squared plus a squared, and see, that was I don't know why I'm putting an a there. This needs to be like this. That is a 3 squared, so that means that this right here needs to be a 3. Okay, sorry about that. Okay, so then you could go ahead and do it that way if you wanted to, like that. All right. Okay, so let's see. I think that's really all I wanted to do with that one, is you don't have to do that one with a trig substitution because there's not a square root in it. So I wanted to just kind of wrap this up here a little bit. And this very last page is just sort of a summary of how these things go. Then we'll take a break here. So what I wanted to go ahead and look at is just kind of how the triangles go like this. So generally what you do if you have x squared plus a squared, now the way I remember this is like this. Since that's a plus, that's what makes that the hypotenuse. Okay, so I'm just trying to show you on this page kind of how you can try to remember all this stuff, because there's 3 substitutions. So that means that the x squared plus a squared is going to go there. So this is going to be a tangent substitution. So it goes like this. That's theta. And then tangent of theta, see, you always want your x in the numerator. That's how I always remember this. So that means since tangent is opposite over adjacent, that means that we want the x there and we want the a there. So that means that we would have tangent of theta is x over a. Then if you solve both sides, if you solve that equation for x, what you get for your substitution is x is equal to a tangent theta like that. Okay, so that's how I remember that, is because there's a plus sign, that makes that the, and then that's got to be a square root like that. That's got to be a hypotenuse. Okay, does that make sense? If it has a minus, then it's either going to be a sine or a secant. Just depends on which order they go in. Okay, so the way I look at this next one is kind of like this. Okay, since that's got a minus, then that means it's either got to be in one of the 2 legs. Okay, now if you do a sine on this one, okay, and again, what you want to have on this is you want to have the sine is you want x over a. Okay, you always want x over a in your trig substitution. Okay, what's the definition of a sine? It's opposite over hypotenuse. So the thing is, where does the x go? The x goes there. The hypotenuse goes there. That's a. And then that leaves you with this part right here being the square root of a squared minus x squared. Like that. So that's how the triangle would set up. Then if you solve for x, you can multiply both sides by a, and then you get the substitution x equals sine theta like that. Okay, so that's how that's going to go. Okay, you guys see how I'm trying to get you to think through this? So that you don't have to, you want to get this memorized, but you want to reason it out. And the next one, again, since that's a minus, that means that it has to be a leg. It can't be a hypotenuse. So the last one we looked at was the secant. So here's how the secant substitution goes, is like this. So you say secant, remember secant's hypotenuse over adjacent. Okay, you want the x there. So you always want it as x over a. If you keep that in mind, it'll help you remember this. So where's the x go? Hypotenuse, right? Okay, where does the a go? Adjacent, so it's got to go that way. And then the leftover one would be square root of x squared minus a squared like that. Okay, so you always have x over a as your trig function. And then if you multiply both sides by a, what you're going to have then is x is equal to, for your substitution, a secant theta like that. Okay, so try to think of it that way so that you don't have to, just kind of blindly memorize this. Again, if it's a plus, hypotenuse. Okay, does that make sense? Okay, if it's a minus, it's got to be one of the two legs. And then if you just reason out x over a, that's got to be a sine because it's opposite over hypotenuse. This has got to be a secant because that's hypotenuse over adjacent. And notice you always have x over a. Why do you have that? Because you want to have this solve for x. You always want that x in the numerator. Does that make any sense? Okay. Okay, and then once you have that kind of put together, it's mostly when you do your substitution, you plug everything in, you use basic identities to get everything put together. And that's the basic idea on that then. Okay, so that should wrap that up. I'm going to go ahead and